Can you see the screen? Yes or no?
Yes, sir.
So in the last class, we actually studied about this orbitals. In the last class, we have studied about the s orbital, p orbital, and the d orbitals. We had studied about their structures. We had seen also from our website the shape of each of them. We will discuss something about this orbital. Then move on to the next. So that means just let's write everything in short. What we have learned about orbitals till now. That s orbitals only of one type. S has only one orbital. P has three orbitals. D has five orbitals, whereas the F has seven orbitals. How many electrons can an orbital hold? An orbital can hold a maximum of so an orbital can hold maximum of two electrons can be there in an orbital. So that means S S since it has only one orbital can have a maximum of two electrons. One orbital, a maximum two electron can be present. As the s electron has only one orbital, can have a maximum of two electrons. But for p function, since it has three orbital, px, py, pz, p has three orbital, can have a maximum of 3 into 2, that is equal to 6 electron. Then for the d subshell, as it has 5 orbital, 5 orbital can have maximum of 5 into 2, that is equal to 10 electron. What about the F? Total 7 orbital. F side subshell 7 orbital can have a maximum of 7 into 2, that is equal to 14 electron. Even by the orbital concept also, we can reach to our table which we have done. This one. The SA Duto p orbital can have 6, the d subshell can have a maximum of 10, while the f subshell can have a maximum of 14 electrons. Using in this way also we can say that S has 2 electron, P has 6 electron, the d subshell has a 10 electron, whereas finally the f subshell has 14 electrons. Now let us see about, now so we are saying something about orbitals. Whereas in the lower classes we had read much about orbits. So what is the basic point of difference between orbit and an orbital? This is something which comes in your school exam. Write down the difference. that is orbit and orbital. The first point of difference can be that what is orbit? It is a well defined circular path, well defined circular path around the nucleus, around the nucleus, in which the electron revolves. Whereas what is an orbital? That is, it is a 3D space. It is the three-dimensional space where the probability of finding the electron maximum. Closer the dots, as we wanted to see yesterday. Closer the dots, higher is the probability of finding the electron. Further the dots, lesser the probability. So orbital is basically a probability region. Then number two, that orbits we know, we have learned from a lower class, that these are circular in shape. Circular in shape. Circular in shape. Whereas orbitals are of different shape. S orbital, spherical, they do not have a fixed shape. Their shape changes. P is dumbbell, whereas the D double dumbbell. As you can see, the shape of this orbital is not fixed for everyone, slightly different for every orbital. Now, what does an orbit represent? It represents that an electron revolves around nucleus circular plane or in one plane, two-dimensional concept. Whereas uh, orbital says here the electron, as we have seen yesterday, here the electron can move three-dimensional plane. That is, can be along the x-axis or the y-axis or even along the z-axis. And what is the maximum number of electron in an orbit? Max number of electron in orbit, that is equal to 2n square. This is the formula. Whereas max number electron in orbital, that is equal to 2. So these are the point of difference between orbit and orbitals. This difference is important for the view from the viewpoint of your exam. Comes in exam. Okay. Now we'll come to the last quantum number, which is a spin quantum number. And luckily, this is not so big, just a small one-line just thing. It is the spin quantum number. Spin quantum number. Noted by S. Spin quantum number can have only two possible values. That is, it can have either plus half or minus. It can have two values. It can be plus half or it can be minus half. Now, what does this represent? We are saying the plus half and minus half, but what exactly can we get to know from this data? Or what in fact is the spin of an electron? So you see that whatever Earth do, suppose if this is the Earth, so the Earth revolves around the Sun. The Earth is revolving around the Sun, but while revolving around the Sun, the Earth is also spinning in its own axis. The Earth is also rotating in its own axis. So the Earth revolves around the Sun as well as it is constantly rotating along our axis. Right. So for electron also same thing happens, that the electron revolves around the nucleus, but it also spins axis. So the spin quantum number refers to this rotational motion of the electron. So then what does the plus half and minus half represent? It just represent, now see the thing can rotate either clockwise rotation or anti-clockwise. So the electron can rotate either clockwise or anti-clockwise. So this plus half and minus half just represents that only, that whether the electron is rotating in a clockwise direction or anti-clockwise direction. Now the thing is, it is not fixed as such. Plus half means clockwise, minus half means anti-clockwise. The values is not fixed as that. It just represents one refers to clockwise, the minus refers to another. Now you can take the plus half to be either clockwise or anti-clockwise. That is up to you. But what it means actually is that if one is clockwise, another will be anti-clockwise. So that is the significance of plus half and minus half. So let's write it down, just that line. A spin of an electron, spin of an electron, spin of an electron represents the clockwise or the anti-clockwise motion of the electron. in its own axis. This is your in quantum number. Okay, so these are the four quantum numbers that you have done. Principal quantum number, then azimuthal quantum number, magnetic quantum number, and finally the spin quantum number. So I hope it is clear to everyone. Is all the four quantum numbers clear to everyone? Yes or no? Have any problem in any specific quantum number?
No, sir.
Completely clear.
No, sir.
So then we have done the quantum number. So now we have just learned three more rules and then we can write the electronic configuration. So now we will see. Now basically the rules are just a guideline to how to write the electronic configuration. Now our topic will be electronic configuration of elements. Electronic configuration of elements. Electronic configuration of elements. Electronic configuration of elements. So the first principle we are doing is called the Aufbau principle. Aufbau principle. Now Aufbau is not the name of any scientist. It is just a German word. The meaning of the word Aufbau in German means building up. It's not the name of any scientist or a it is just a simple German word which means building up. So let's see the principle. According to Aufbau principle, according to Aufbau principle, well, are you writing down these notes? Is everyone writing down a note after the class?
Yes, sir.
That is forwarding you the notes. So,
Yes.
Yes, sir.
according to Aufbau principle, electrons are filled. Electrons are filled in in various orbital in order of their increasing energy. In order of their increasing energy. Increasing energy. So that means electron will be filled from a lower energy to higher energy. First, the orbitals which have low energy, first the electron will get filled over there. Then the orbitals having the higher energy will actually get the electron. So how to remember which orbital has a lower energy and who has a higher energy? It is certainly not possible to calculate so much. Then we did some shortcut techniques to remember which particular orbitals has a lower energy and how it increases to a higher energy orbit. For this one, we need to draw this pyramid kind of structure. One is, you have to draw it in exactly this way. Then below it, 2s, 3s, 3P, 3D, 4S, 4P, 4D, 4F. Now see, why am I not writing anything called 2D, 2F, 1P, 1D, 1F? Because yesterday we have seen that such orbitals cannot exist. From the azimuthal quantum number, we have seen that can be till n minus 1. So if you are confused, then see the azimuthal quantum number. 4S, 4P, 4D, 4F, then 5S, 5P, 5D, 5F, 6S, 6P, 6D. Okay. So now what do we do? Now we draw this line in this. Okay. So what does this line mean? Suppose this is one person. So if he starts walking along this path, if he's starting walking along this path, then which orbital comes first? 1s. If he starts walking over here, then what will first come? 1s is going to come at first. Then once he reaches the end, again he goes the beginning of the line and starts walking. So first you are getting 1s, then again you are going back. You will encounter 2s. Then again you go back. Now you will get 2p followed by 3s. Then get to 3p. Then 4s. Then 3d. Then 4p. Then 5s. Then 4d, 5p, 6s. So this is how this is how electron occupies the orbit. So first, what will the electron occupy? 1s. Then electron will come in 2s orbit. Then electron is going to come in 2p, then 3s, then 3p, then 4s. Then electron is going to occupy 3d, then 4p, followed by 5s. So this is how the electron is going to occupy the orbitals. So this is a way by which you can remember the order of occupancy without memorizing, because you can just draw the pyramid quickly and quickly find out the order in which the electrons will be filled in. So the order of increasing energy is going to be 1s has the least amount of energy. So the first electrons will always come at 1s. Once 1s is completely filled, once 1s is completely occupied, then the electron will go in the 2s orbit. Then the electron will go in the 2s orbit. Then once electrons in the 2s orbital is completely filled up, once the 2s orbital is also filled up, then electron will go in the 2p orbit. Once 2p is also filled up, it will go to s orbit. So like this way the electrons will fill up. After 3s, 3p is filled up. Then 4s, then 3d, then 4p, followed by 5s, then 4d. Then you have 5p. Then 6. So this is the order in which the electron is getting the field. Okay. Obviously, once the previous orbital is filled, then only the electron will go to the next orbital. When 1s is filled, then only electron will go to 2s orbital. After completely filling of 2s, then electron will go to the 2p orbital. It is not like, say, 2s is incomplete and yet the electron goes into 2p. That type of situation is not. First, the orbitals which are present before, they have to be filled in completely. Then only can the electron move on to the next orbit. So this is the Aufbau principle. It is as if, suppose that kind of we have an auditorium kind of situation. And suppose this is an auditorium. This is the stage, and these are the rows of seat. These are the rows of sitting arrangement in the auditorium. So the situation is something like this: that the first row of seat is called 1s, then you have 2s, then 2p, then 3d, like this way. Sorry, not of them. 2s for not. So once all the seats in the first row gets filled up, only then will a person go to the second row, because everyone wants to see the performing artist from a close distance. So that is why once the first row of seat is filled up, only then will the electron go to the second row. It is not like the people will just sit out random. Everyone will try to sit in the best possible place, in the as front as possible. So that is why once the first row in the auditorium is filled, then only will the second row, that is the 2s, that is filled. Once 2s is filled, then only the person will move to the third row, which is the 2p. So this is how the electrons are filled up in an orbital according to Aufbau principle. So is the Aufbau principle clear to everyone?
Yes, sir.
Yes, sir.
About the others?
Yes, sir.
So no doubts there. Then let us see the next principle, which is Pauli's exclusion principle. So now the next principle that we will do is the Pauli's exclusion principle. Pauli's exclusion principle. So what does the principle say? That no two electron, in an atom, in an atom can have exact same set of 4 quantum numbers. So what does this Pauli's exclusion principle say is that this is just like everyone might be living in Andaman, everyone is living in North Andaman. It might happen that two of you live in the same locality also, but it never happen that two of you live in the exact same address. That is not possible. Everyone's address is different from one another. Even if you live in the same locality, still there will be a difference. So no two of you can have the exact same answer. So here also, no two electron in an atom can have the exact same set of quantum numbers. That means the four quantum numbers cannot be similar for two electrons. It has to be different. It has to be different for each and every electron in that atom. Even if suppose let us take a situation. Suppose this is one electron, electron number one. Let us say electron number one. And we have another electron, which is electron number one and electron number two. So what does this electron number one and two represent? Suppose let's take here the principal quantum number value is 4. The value of L is 0. That means S subshell. That means M is also equal to 0. Here also the value of L is equal to. Here also the value of L is 0. M is equal to 0. So you are seeing out of the four quantum numbers, 3 are completely similar. But always the fourth one will then be dissimilar from each other. S equal to plus of this one, you are getting S is equal to minus. So even if we find that the three are becoming similar, there will certainly be a difference in the last quantum number, that is in the spin quantum. Yes, there can be, it can be completely different also. Even if in a tricky situation, if you find that all the quantum numbers are becoming similar, that means 4 out of the 3 are becoming similar, then the last one, that is the fourth one, will be guaranteed to be different from one another. This is what the Pauli's exclusion says. Then you have the last principle, which is the Bool's rule of maximum multiplication. Bool's rule of maximum multiplication. For this one, I will write down the rule first, and then we'll explain it once we do the configuration. Bool's rule. Bool's rule of maximum multiplication. What does this Bool's rule say? Let's see. This says no electron pairing, no electron pairing takes place. No electron pairing takes place in orbitals, in orbitals until each orbital in the given suction, until each orbital in the given suction contains one electron each, contains one electron each, and the spin of any unpaired electron pair. So we will explain this once we do the configuration. And another rule of Moore's is half filled, half filled, and full filled configuration, half filled and full filled configuration are more stable. Half filled and full filled configuration are more stable than neighboring configuration. Half filled and full filled configurations are more stable than neighboring configuration. So this is the second rule of Moore's. So now let us write down the electronic configuration. The electronic configuration okay. So first we'll start with the simplest one, that is hydrogen. So what is the atomic number of hydrogen? What is the atomic number of hydrogen? 1.
1.
This is hydrogen. So before you used to write hydrogen as only 1. You wrote the configuration of hydrogen to be 1. But now, because hydrogen has only 1 electron, atomic number of hydrogen 1 means hydrogen has only 1 electron. So now, once you know the Aufbau principle, so where will the first electron come? The first electron will be coming at the first row, that is the 1s orbital. The first row occupying the 1s orbital. So it will be written as 1s, 1s. This is to write how you write the configuration of hydrogen. That is 1s1. Now, if you want to make a box diagram, okay. So you can write this 1 electron either in this way, or you can write it in this way also. That is totally up to you. Whether you put the arrow upside or downside, that is totally up to you. You can write any one of the representation is completely correct. So this is the 1s orbital. So it is not possible to always draw the structure for quick answering. So that is why it is not possible to draw the three-dimensional graph and draw the spherical shape of the s orbital. So that is why we refer to this orbital in this box diagram, boxes. So the 1s orbital has only 1 electron. That is what the box diagram is showing. Either of the drawing is correct. Now let us see the second atom. Second atom is called helium. So atomic number 2 is helium. Now helium has 2 electrons. And before you wrote the configuration, simply 2. You wrote it as. But now according to the Aufbau principle, where is the first 2 electrons sit? It will sit in the 1s orbital only. That is why the configuration of helium is 1s. Because what did I say? Electron will go to the second orbital, that is the 2s. Only if the first row is completely filled up, only then will the person go to the second row. But over here, the first row is not completely filled up. That is why the 2 electrons will both be present in the 1s orbital. So it is saying 1s2. That means the 1s orbital contains 2 electrons. So this is what this symbol means. So now if we draw the box diagram, what will it be? Now this can be showed as one upside and one downside. Or you can do the ulta also, that is first down, then you can show up also. Or someone of you might say that I want to show it in this way, that both are upside arrows. Both the arrows are upward. But this is not possible. This is not a correct structure. Why? Let's see. Because see, for this electron, the value of n is 1. The principal quantum number is 1 over here. The value of L is equal to 0. That means the value of M is also equal to 0. For this electron, you see, N is equal to 1 because this is also present in the 1s subshell only, 1s orbital only. L is equal to 0. M is also equal to 0. But see, this 1 is an upward arrow. So that means you can consider this to be S is equal to plus half. And over here, it's a downward arrow. So S is equal to minus half. So over here, this follows the Pauli's exclusion principle. Even though the first 3 quantum numbers are similar, the last quantum number, there is a difference between them. So that is possible. But if you draw both the arrows upward, that means what? N equal to 1, L equal to 0, S is also equal to 0, sorry, M also equal to 0, and S is equal to plus half. And this one is also upside arrow, that means N equal to 1, L equal to 0, M equal to 0. And since this one is also upward, that means this will also have the same value of spin. So that means if we do this box diagram, then it actually indicates that all the 4 quantum numbers in an atom is similar, which is not possible as it violates the Pauli's exclusion principle. That is why this type of box diagram is not possible. Okay. So in a box diagram, one has to be an upward arrow, another one has to be a downward arrow when pairing is taken. Okay, so is the configuration of helium and why we are drawing the box diagram in this way? Is it completely clear?
Yes, sir.
Yes, sir.
This is very important. This is like the ABCD of chemistry. Be very, very clear with your concept. This is violating the Pauli's exclusion principle. But this one you can draw. So either of these two is acceptable. You can draw it in this way also or this way also. But this is not acceptable as it is violating the Pauli's exclusion principle. Okay. Now let's see the next one. So now atomic number 3 is lithium. So atomic number 3 we have lithium, Li. Previously you used to write the configuration of lithium as 2,1. This is how you used to write it before. But now we'll be writing it as the first electrons will occupy the So what will be the configuration? You cannot write 1s3 because see, we have already done it multiple times that the S subshell can have a maximum of 2 electrons. Here also we have calculated, and yesterday also we have calculated this in the table, that is this one, that the S subshell can has a maximum of 2 electrons. One is a maximum 2 electrons can be present. So that means the first row of the auditorium is now completely filled with 1s2. If the first row is filled, then electron will go to the second row, that is 2s. That's why the configuration is going to be 1s2. Now this is completely filled up. Now what about the third electron? It will go to the next orbit, that is 2s1. 1s2, 2s1. This is the configuration of lithium. If we draw the box diagram, it is going to look like this. One, two, three. 1s, 2s. This is a lithium. Then let's draw beryllium. So beryllium has an atomic number of 4. So Be is your beryllium. Previously, you used to write it as 2 common, but now it will be written as the first 2 electron occupies the 1s orbital, so 1s2. Then the second 2 electron occupies the 2s orbital, 1s2, 2s2, 1s2, 2s2. That means you will write it in this way. Well, if in your exam, if they're just saying you to write electronic configuration, no need to draw the box diagram. Box diagram are for the sake of your understanding. Or if the question specifically asks you to draw box diagram, then you obviously have to draw. But if you just write the electronic configuration, then there is no need to draw the box diagrams. So beryllium is done, 1s2, 2s2. Now what about boron? Boron has an atomic number of 5. So boron has an atomic number of 5. Boron, you wrote it before as 2, 3. But now we are going to write it as 1s2, 2s2. Now why is it 2s2 and not 2p3? Sorry, 2s3? Because again, the s orbital can hold a maximum of 2 electron only. S subshell can hold a maximum of 2 electron. So that means now the first 2 seat of the auditorium is filled. 1s has been filled, 2s is also filled. So then person will go to the third row, that is in 2p. Now the electrons will start filling up in 2p. So that is why the configuration of boron is 1s2, 2s2, 2p1. 1s2, 2s2, 2p1. Now what is the maximum number of electron in 2p? 2p can hold, see we have done it yesterday. 2p can hold a maximum of 6 electrons. 2p can hold a maximum of 6 electrons. And from the magnetic quantum number also we have seen that the p orbital has p has 3 orbitals, px, py and pz, where each of the orbital is capable of holding 2 electrons each. So that is why 3 orbitals contains 2 electrons each. So 3 into 2, that is equal to maximum of 6 electrons. So now let's draw them. Now let's draw the box diagram. This is for 1s, the box diagram of 1s. Now see the p subshell has 3 orbitals. So that means I need to make 3 boxes for this. Previously S didn't have any other orbital, it has only one. So that was only one single box were drawn. But p subshell has 3 orbitals. So that is why 3 different boxes has been made of it. So that is why this is 1s, 2s, 2p. Now you write 1s2, 2s2, 2p1. Done. Now you will now tell me what will be the configuration of carbon. What is the electronic configuration of carbon? Tell me. 2, 4. Tell. Don't be afraid.
1s2,
Then
2s2,
yes,
2p2.
1s2, 2s2, 2p. So this is the electronic configuration for carbon. So now if you draw the box diagram, how will it be? The first, second, then you draw the p orbital. Then you have the p orbitals. One is yes. So 1s has 2 electron, 2s 2 electron, and the 2p also has 2 electron. Now tell me how will the electron look? Will I draw the electron like this? Should I draw it like this? Should I give the 2 electrons like this? Or should I draw it like this, where both the electrons are looking upward? Or should I draw it like this, one up and one down, but in different boxes? So how should the electron be drawn? Should both the electrons be in the same box? Should they be in the different box looking at the same side? Or should they be in different boxes, but the spin is going to be different? So what should be drawn over here in the boxes? So for this one, we will be taking the help of Hund's rule. Now let's see what does the Hund's rule say. The Hund's rule says that no electron pairing takes place in orbital until each orbital in the given subshell contains one electron each. So it's basically, if you consider these to be as rooms, if you consider each of the boxes as room and the arrows as a person, so what will happen is that everyone wants a single room, everyone wants a private room to himself. That is why first all the boxes will be filled with one electron. Only after that pairing will take. So first all the boxes will be occupied by single electron. Once all the boxes has been occupied, only after that will double occupancy of electron in the orbital take. So that's why we cannot, this structure is not possible. This diagram is not possible. That means if you draw it in this way, this is not possible because here you are doing pairing of electron even though the other boxes are still empty. So this is not possible. So what you have to draw is one electron in this box and the second electron in this box. Another question is, will it look upward? Will the arrow be upward or downward? So that is also explained in the Hund's rule. You see, the spin of unpaired electron are parallel. So they has to be in the same spin. So if this one is upward, then this is also going to look upward direction. Then this is also going to look upward. So this is the box diagram for carbon. Okay, is it understood? Why you wrote it in this way? Why the box diagram is done it in this way? Is it clear?
Yes, sir.
Yes, sir.
Then let's take the number 7, atomic number 7, which is your nitrogen. Which you previously wrote it as 2,5. But now you will write it as 1s2, 2s2, 2p3. Now if we draw the box diagram, how is it going to look? First box, 2s. So there are 3 electrons. So 1 electron, electron, 3 electron, because according to Hund's rule, first single occupancy of electron will happen in the orbital. Okay, so that is why we get this done. Now see number 8. But before that, you see p orbital, p subshell can hold a maximum of 6 electrons. And in nitrogen, we are getting there are 3 p electrons, p3, whereas p can have a maximum of 6 electrons. So that is why we say p is nitrogen to be a half filled configuration, because the p shell in nitrogen has half the total number of electrons possible. So this is a half filled situation. This is a half filled orbital. And Hund's rule says that half filled configurations are more stable than the others. So that is why from your lower classes you have seen that nitrogen does not undergo much reaction. Why is it so? Because nitrogen has a half filled configuration, and that is why it has a higher stability. So it doesn't undergo so much of reaction. Then what about oxygen? Oxygen is 2,6. 1s2, 2s2, 2p4. 1s2, 2s2, 2p4. Now what will happen? The first box, 2s, p4. So 1s2, 1s2, 2s2. Now 2p4. So 1, 2, 3. So now all the rooms are filled with single occupants. All the orbitals have single electron. So now where will the fourth electron go? Now nothing to do. It has to pair up. So now the fourth electron will come. This will be the fourth. So now let's draw number 9, which is fluorine, which you before used to write it as 2,5. Sorry, 2,7. So that is 1s2, 2s2, 2p5. So this I'm not drawing the box diagram because it's similar only. That here you will get another electron will get added up to the 2p orbital. Other than that, the box diagram will be completely similar to that of the oxygen. 1s2, 2s2, 2p5. Then you will get number 10, that is neon. So neon is a noble gas, you know, 2,8. The configuration of neon is 1s2, 2s2, 2p6. 1s2, 2s2, 2p6. It is going to look like this. One s2, 2s2, 2p6. So 1, 3, 4, 5, 6. This is the configuration of neon. Now you see that all the position in even the 2p, all the position in the 2p orbital is filled up. 2p can hold a maximum of 6 electrons, and with neon, all the positions available in the 2p orbital is also completely occupied up. So that means now there is no more space in the 2p orbital. The 2p orbital has full filled configuration. And Hund's rule also says that full filled configurations are more stable. Full filled configurations are more stable. And that is why neon we know is a noble gas, which is extremely unreactive. It doesn't undergo reaction. Why? Because neon has a full filled configuration. And according to Hund's rule, full filled configurations are extremely stable. So neon does not undergo reaction. Now we see that even all the orbitals till 2p is completely filled up. 1s completely filled up with electron. 2s is also completely filled up with electron. now 2p is also completely filled up with the 6 electrons. So now what will be the configuration of sodium? That means where will the next electron go? So the next electron will go in the next orbital. So what comes after 2p? Now it will go to the 3s orbital. Now see, in the auditorium, first row is completely filled up, second row is also completely filled up, and the seats in the third row is also completely filled up. So now where will the persons go? They will go to the fourth row. So that means now the electrons will go to the 3s orbital. So in this way, electron goes on filling up. Once 3s is also completely occupied with 2 electrons, because s has a maximum of 2 electrons, then the electrons will move to the 3p orbital. Once 3p is also completely occupied, then the electron will move on to the 4s orbital, and so on and so forth. The electrons will go on occupying as the atomic number of the element increases. So this is the atomic configuration. Now I will be giving you a homework for today. That is, you need to write the electronic configuration from sodium to calcium. Okay. So this is the homework for today, which I need to see by tomorrow. So you have to write down the electronic configuration from sodium which has an atomic number of 11, calcium has an atomic number of 20. So you need to write the electronic configuration for this element from sodium to calcium. It will be exactly similar to like how we are doing. The method will be exactly similar. Since just as the number of electrons are increasing, they will slowly and gradually move on to the higher orbital. After 2p, 3s will come. After 3s, 3p will come. I think you have got the basic hang of how to write the electronic configuration. So this will be the homework for today, which you need to write, and I will do it tomorrow. I will be writing till 30. Yeah, so that's it. Okay. Please do your homework. Please try it out. Don't think that it might be wrong or right. Don't think about that. At least try it out. That's very important. Try right. And electronic configuration, it might appear simple at this moment because see, we are just doing them one after the another. But if by chance they ask you, they will be not asking you in this way. Here we are writing 4, 5, 6, 7. So naturally the electrons are gradually increasing by one. But in exams, you'll be just given a random atomic number, and then you have to write the electronic configuration. So that will require a huge amount of practice. Okay? So that you can write the electronic configuration of any random number. That is why you need to write and practice the electronic configuration. Okay. So is today's class clear to everyone? Is everything about today's class completely clear to everyone?
Yes, sir.
Have you understood how to write the electronic configuration? Can you do the
Yes, sir.
configurations from sodium to calcium? Okay.
Yes, sir.
So then
Yes, sir.
kindly do the homework for tomorrow. Okay. And then tomorrow we will do the other rest of the electronic configuration. I think either by tomorrow or by Friday, we will be completing with this chapter. Okay. Then that's it for today. So then that's it for today.
Sir, tomorrow class is there.
Tomorrow is Wednesday, right?
Yes. Yes, yes, sir.
Wednesday I take class, na? Yes, Wednesday
Yes,
is there.
yes.
Wednesday is it's a scheduled class. Tomorrow class.